Hello everyone, we are CME Group 14 and our project is on pavement and traffic light design on Houbolt Road. To begin, our project site is located in Joliet, Illinois, at the intersection of Houbolt Road and I-80. This location in Joliet is very important as it is home to one of the largest transportation hubs in the nation. Currently, there is a diamond interchange at this intersection, but with the new bridge being built over the Des Plaines River, traffic is expected to increase, so an upgrade to a diverging diamond interchange will be needed. Also, new pavement is needed as the existing pavement would not be able to withstand this predicted traffic, especially since 40% of this traffic is expected to be heavy vehicles. With almost an expected 100% increase in traffic, the level of service on Houbolt Road is expected to drop to a level of service of F. This means delays and congestions will rule this road. The goal of our projects is to prevent this and help the road facilitate the future demand in traffic. We will be looking at both rigid and flexible pavement designs to see which best fits our design. The design life for rigid pavement is of 20 years, and the design life of flexible is only 17 years, since the flexible pavement will not be able to withstand such large volume of traffic for the 20 years. Finally, the predicted ADT of this road is to be 46,000 vehicles in the year of 2040. As you can see here, this is where the proposed bridge is to be built over the Des Plaines River. And this is our project scope, from Canahan Road to Rock Creek Boulevard. Here we see the difference in flexible and rigid pavements. The difference is to focus on how each pavement distributes their loading. Rigid pavement is able to distribute the load over a wide area due to its rigidity and high modulus of elasticity, where flexible pavement uses sets of layers to help with the distribution since it does not distribute it as wide and well as the rigid does.
Looking closely at the rigid design, the mechanistic approach first determines the traffic factor of the road. The road has been classified as a Class 2 with a traffic factor of 78.47. Determining the traffic factor allows us to compare our findings to the minimum required traffic factor, of which was determined to be 4.13. This means we can proceed with the design with a traffic factor of 78.47. The next step in the design process is to choose the subgrade support grading. Given that the soil testing completed by Intero on Houbolt Road was of poor quality, improvements in the design is evidently needed with the proposed increase in heavy truck traffic. Our team has determined that utilizing a tied shoulder with reinforcing steel would be best for this design. Not only does this reduce stresses in the pavement, it also helps increase the load distribution, which helps the longevity of the road. The PCC thickness, according to the graph, is determined to be 11.5 inches. We are now going to take a look at the Ashton modified approach. This alternative design method uses the same traffic factor as the mechanistic approach, however, they differ in procedure. This method only requires a traffic factor, IBR, and the road class type. Using the mechanistic approach and the Ashton modified, the pavement thickness was determined to be 11.5 inches. Our type of PCC results to be continuously reinforced concrete pavement. Since the traffic factor of 78.47 is greater than IDOT's traffic factor of 60.
In this alternative design of flexible pavement, we determined the calculated traffic factor of 45.3 and a minimum traffic factor of 2.64. Currently, the subgrade support grading is in poor quality. The climatic conditions of the area of Joliet appears to have a range of temperatures from -22 to 64 degrees Celsius. The asphalt binder material that can withstand temperatures in this range was found to be PG64-22. The HMA mixed temperature was determined to be 75.5 degrees Fahrenheit. We used the chosen traffic factor of 45.3 to get the corresponding HMA strain value. This value corresponds to 41 microstrain. With the HMA strain and the modulus found in the previous step, it was determined that the poor condition of the road forces a strain thickness of 16.5 inches. IDOT has a limited required thickness of only 15 inches. Considering these terms, the required thickness for the flexible pavement would have to be 15 inches, which means that this alternative design is not acceptable for Houbolt Road.
The modified AASHTO method helped us find the thickness and type of material needed for each layer. From this graph, knowing the traffic factor and IBR, we got a structural number of 6.4, which represents the strength required for pavement in order to perform well with the predicted traffic. The structural number is a sum of the coefficients of the relative strengths of the surface, base, and subbase materials multiplied by their depths. Our structural number was very high, which is why we were limited on what materials to use. Using the table, we got a calculated structural number of 6.4 and a thickness of 21 inches using HMA for surface and base cores and uncrushed granular material for subbase. As mentioned before, IDA has limited the flexible pavement thickness to only 15 inches. Due to this constraint, we decided not to proceed with a flexible pavement because it's not enough for the increase of heavy traffic in 2040. We concluded our final rigid design of continuously reinforced concrete pavement of 11.5 inches.
Now the group will be discussing our next objective, which is traffic lights. We decided that signal timing would be very important because it could help handle the increasing traffic volume and help improve safety. It'll be especially helpful in improving movements with high traffic volumes without the need of additional lanes. Signal timing will help tackle the problem of future congestion and stop the drop in the level of service. Another reason why we focused on traffic lights was because of the shift from the Diamond Interchange to the proposed Diverging Diamond Interchange. Here we have the approach on our calculations for signal timing. First, we established movement groups for each phase. We had 2 phases with 3 movement groups each. Next, we calculated the adjusted saturation factor. Thirdly, the critical lane groups and critical V over C ratio for each intersection were calculated. Finally, we determined the yellow time, offset, and the effective green time for each phase.
Here are equations for the factors that we used to calculate the adjusted saturation rate. Shown is an example of how vehicles coming off I-80 and turning left onto North Houbolt Road. We use the saturation flow rates to calculate the flow ratio, which is later used to determine green times for each phase. Before we were able to determine the effective green times, we had to calculate some variables first, like the sum of the flows for critical lane groups and the effective green times for each lane group. Here we calculated the westbound and eastbound effective green times. Eastbound effective green times had more reasonable times for each phase, so we decided to use those times for the intersections. To obtain a yellow time of 5 seconds, we used variables such as deceleration rate, acceleration due to gravity, and road slope. For offset, the variables needed were travel speed in feet per second and distance of upstream and downstream intersection to obtain an offset of 12 seconds.
To confirm that the interchange would have a passing level of service, we used the software HCS7 to help calculate it. Many of the variables such as vehicle demand, offset, and other variables that were calculated previously were inputted into the software. The HCS7 software was able to provide us with green times for 2 phases and a level of service for each movement. Overall, the level of service of the DDI should be able to accommodate the future 2040 vehicle demand successfully.
For cost estimate, we decided to focus in on the pavement design. We can see that the initial price of our rigid pavement design is of $4,051,183. When looking at the flexible pavement, we can see that the initial cost is of $3,657,604. We can see the noticeable difference in price, but this makes sense since flexible pavement is known to be cheaper to construct, but it is worth noting that the maintenance for flexible pavement is higher than that of rigid pavement. When looking at the total life cycle cost analysis, we can see that the cost of pavements come out to be almost the same, even though their initial prices are different.
When considering sustainability, a major method of sustainability would be through the use of recycling asphalt. Reclaimed asphalt, or recycled asphalt, is one of the most repeatedly reused and recycled materials, as its widespread use in many road projects has significantly increased over the years. This can result in ways of controlling significant raw material cost reduction, as well as other project expenses.
Using Revit, we constructed a 3D model representation of the proposed Diverging Diamond Interchange. Here are a few views. We have the side view, eastbound view, westbound view. That concludes our presentation. We are CME Group 14. Thank you for your time.